Hey, everybody. Good morning. Happy Sunday. Hope that you're doing well. Thank you so much for spending another Sunday with me here, learning about neural networks and continuing our whole series of live streams on data science. So glad that we get to spend the time together. We are making great progress on our quest to keep on learning about neural networks. I think that we are nearing the end. We can kind of sort of see the end from where we're at, but really we've been doing really good progress, but there's still a couple of things that I want to get across to you guys. You know, when I start these series, I kind of sort of have a map of where I want to go with things. Like, I know what I want to teach, I just don't always know how to get there. And that makes it difficult for me to estimate the number of hours and sessions that we're going to need for this, right? But I think we're getting close to a finished state. But at the same time, there's some things that I just don't want to leave you without teaching, right? Like there's got to be some things I get across, right? So we're just going to see how today goes. We're going to see how next week goes, and then kind of go from there. And then we'll pick up another series. You know, right now I'm going to probably do a series on robotics. Some people have requested that. So if you guys want to think about a series beyond that, let me know. But that's where we stand now. Also, I should let you guys know that for some reason, just like last week, the streaming on Instagram just refuses to work. I don't know what's going on there. I'm going to have to investigate that after this this stream, and I might have an Instagram only live stream real quick just to say hello to everybody. But for some reason, Instagram just does not want to cooperate on the live, so we'll see how it goes. I'm seeing people in the chat already. Thank you so much for that. Feel free to say hello. Let me know just if you want to check in. Your chats are going to appear over here, and as always, I'm also streaming on Kick and Twitch and X. So if you're on those platforms, say hello also, and we'll all appear here in the unified chat. But I am excited to kind of go through the materials on what we have today. It's probably going to be a little bit of a longer session is what my gut tells me, but who knows? We'll see. We'll see. As always, we're going to have as much participation as possible, so feel free to give your answers when I ask, or any questions you have or anything else, just let me know, okay? It looks like I have a little dog here on me there. All right, so let me look in the chat here. Jay Moo. Jay, so good to see you. Guys, if you see a special icon next to Jay's name, that's because it's a member of the YouTube channel. So Jay, thank you so much for your continued support. Really appreciate you. Jay says, good morning from Dripping Springs, Texas. I'm assuming by Dripping Springs you're not referring to the rain, because this is not the rainy season in Texas. So I hope you're doing well out there, Jay. Jay, if I remember right, I think you're outside of the Austin area, if I remember right. Dripping Springs. So that doesn't sound like Dallas, like the Metroplex. But good to see you, Jay. And glad you're here, and let us know how you're doing. Starry Vibes, our good friend Starry Vibes says, hello, sir. I hope you're doing well. I'm doing very well, thank you. Hope the same for you, Starry Vibes, and your family and your classes and all that good stuff. It's been a good week. It's been a busy week. It's been really hot where I live. The weather is definitely summertime here. But we also had some rain earlier in the week, which is really weird. But I'm doing well. Thank you so much. You know, I usually go into the weekend strong, because on Fridays is when I do my check-ins with all of my coaching clients. You know, I talk to them throughout the week, of course, but every Friday I make sure that I check in with every single coaching client. So, you know, and that's one of the funnest things that I do. So it always puts me in a good mood for the weekend. So I did that yesterday. Everyone is doing well. So if they're doing well, I'm doing well too. Yassine says, hello, sir. It's Yassine from Tangier, Morocco. Yassine, so good to see you. How are you? Hope you're doing well out there. When do you guys reach the end of classes? Aren't they soon? I mean, I would hope that you're out by now, right? I mean, it's already June. In the US, if you're graduating, you finish basically the first week of May, maybe even earlier in some cases. And then if you're just a regular student, you're not graduating, you probably still don't go longer than the middle of May. So I wonder how that is in other countries. So I hope that anybody in the chat who, is still in college is hopefully out by now. Denelson, our good friend Denelson says, "Good morning, everyone. How everyone is staying? Hope everyone is staying safe and enjoying their days." Denelson, thank you so much. I appreciate that, and same to you. Hey, Denelson, by the way, I did send you a message on LinkedIn if you wanted to take a look at that. But hope you're doing well in LA, Denelson, and glad that you're here. Thanks for the support. Manoj, our good friend Manoj says, "Good morning, Sir Dennis and everyone. How's everyone doing? Happy Sunday." Happy Sunday to you too, Manoj. Gonna be a good Sunday. If you guys remember, I've shared that I sometimes make myself a cabbage soup. So right now I have my soup cooking. I can smell it already. So as soon as this is done, I'm gonna shut down the stream. I'm gonna go eat and enjoy the rest of my day. So hope that you're having a good Sunday too, Manoj. Let us know how you're doing. Ayush, I want to say that it's your first time here. I don't recognize the name. Ayush says, "Yo, what's happening?" Okay, a very casual introduction. That's okay. Ayush, you have come across my Sunday stream. That is my usual time when I have a series that I like to cover, like a bigger data science series that takes multiple live streams. And that's what we're doing today. We're kind of in the closing stages of our series on neural networks. You're welcome to go to YouTube and look at all the parts in the playlist. I have a playlist just for this series and really for all the series that I've done. But that's where you're at, Ayush. That's the goal of today. Today we're going to just continue learning what we have on neural networks. Kind of keep on building upon it. You know what I mean? Let me skip ahead. Ayush says, "Soup sounds tasty. Sunday, yes, it's my first time here. You are taking neural networks class, type something." Yeah, it is a neural networks class, Ayush. Hopefully some of these things will make sense to you, and if they don't, feel free to go to the earlier series or just keep on coming back. But yeah, we're going to focus on neural networks today for sure. Manoj says, "I'm doing good, Sir Dennis." Good, Manoj. Glad to hear it. Glad you're here, my friend. Shan, I believe this is your first time here. Welcome. Feel free to let us know where you're from. Shan says, how do you apply psychology in data science and machine learning?" That's a little bit too broad of a question to really try to answer effectively. I think you're going to have to kind of narrow that down a little bit. Are you talking about data from psychology, or the psychology of having people using algorithms, or... I mean, there's a lot of ways to interpret that question, right? And I don't want to speculate on that. So let me know what you mean, Shan. Ayush says, "That sounds great. I'm excited." Well, good, Ayush. I'm excited too. I'm always excited to share different materials with you guys. See how it comes across. Sometimes some material goes over better than I anticipated. Sometimes it doesn't. But either way, we're here to have fun. We're here to live in the community of data scientists, right? Because data science is something that we should be sharing and talking about and getting different perspectives from people, right? That's a big part of data science. Hey, I see it this way. How do you see it? Oh yeah, why do you say that? That's an important part. So glad you're here, Ayush. All right, for anybody else that's in the chat that wants to say hello, now's the time for it. Otherwise, I want to go into the slides or into the presentations because I think we're going to be spending a little bit of time together today. I don't know if it's going to be a longer session today. It feels like it, but we'll see. Osama, our good friend Osama says, "Hi, sir. Happy Sunday. Hope everything is going well from Morocco." Yeah, of course, Osama. Everything's going real well, and of course, remember you're from Morocco. I think you said you're from just south of Casablanca, right? I think it was Satat. That you were from. Remind me if that's correct. But glad to see you here, Osama. Glad you're well. Let us know how things are in Morocco. I assume it's getting a little warmer there also, just like in most parts of the world, or at least in the northern hemisphere, right? But anybody else who wants to say hello? Last call for it. Otherwise, we're going to get right down to it. Right down to it, guys. So let me prep my desktop, make sure I got everything I want to show ready. Um, Osama says, yes, sir, from Satai. Okay. I figured. I that's what I had remembered. You know, I may be old, but some things up here still work, guys. All right. All right, let's get started with our lightning round review for our latest installment on neural networks. I have some questions up on the screen. Now, some of these might look familiar because we did have some of them last week, but there's also a lot of new people in the chat. So why don't we start with these 4 questions? What is a learning rate? Are there different types of neural networks? When would you use each one? What is a grid search? And is every grid search successful? What are some of the frameworks that are used for neural networks? And why do we never use PyTorch? All right. So, those are the 4 questions in front of the group right now. Feel free to put your answers in the chat below. But what do you think? Why do we have, what are the answers that we can put with some of these 4 questions? I'll give you guys a minute to think about it. You don't have to answer all of them. You don't have to answer in order. Just pick one that you feel most comfortable with and go for it. I'm going to have to figure out why the Instagram is still acting up, just like it was last weekend. But we've had a lot of growth on Instagram recently, so I'm going to do a special stream just for them after this. But until then, let's think about these 4 questions. What is a learning rate? Are there different types of neural networks? What is a grid search? And what are some of the frameworks used for neural networks? And by the way, that last one's important because today I do want to focus on using frameworks. We've been using raw code, which is great, right? I'm a fan of that. But let's get a little bit more modern today. We're going to start using some frameworks. So let's see how comfortable you guys are with these 4 questions. What do you guys think? Feel free to put them in the chat. Okay, Starry Vibe says learning rate controls how much the model's weights are updated during training. Okay, yep. That's a pretty reasonable answer. Starry Vibe says, are there different types of neural networks? Yes. Okay, Starry Vibes, give me at least one if you don't mind. Give me at least one. And if you're too shy or don't know the answer, you can just say, I agree with Starry Vibes, I disagree with Starry Vibes, whatever you guys want here. Okay, Manoj says, grid search, tuning hyperparameters by exhaustively trying combinations from a predefined set of values. Grid search is tuning hyperparameters by exhaustively. Yeah, that's a pretty good definition. What do you guys think? Yassine says, yes, for number 2, he says, yes, there are many types of neural networks. Like RNNs, CNNs, we use each one depending on the data and the problem at hand, and more specifically, data dimensions. Okay. I like that, Yassine. I like your answer. We're going to come back to it because I like the way you closed out the answer there. Denelson says, a learning rate is how fast or slow a model learns from its epochs. It can either take big steps or small steps after each epoch to find a minimum. Okay, Denelson, Denelson, is it more desirable to take smaller steps or bigger steps? Because you say what it can do, big steps or small steps. but that doesn't tell me which one is more desirable. What do you think? Okay, Starry Vibe says for the different types of neural networks, CNN, FNN, and GANs. FNN. Did you mean to do FFN, maybe? I don't know of an FNN, but maybe I'm just wrong. But I think you meant FFN. And then also Starry Vibes mentions GANs. So that's an interesting mention. So if anybody in the chat, what does GAN stand for? We haven't seen that one yet before, right? We haven't seen that one. So if somebody wants to give me the definition for GAN, G-A-N, go ahead and put it in the chat, okay? Michael says, happy Sunday, Dennis and Eric. Michael, so good to see you. How are you, our good friend? Michael, I believe that you are from Nigeria, so welcome back. Glad you're here, my friend. Yassine says, grid search is a method to experiment with different combinations of hyperparameter values. Yeah, I like that. I like that. Yeah. Okay, Starry Vibes is a feed forward neural net. Okay, yeah, so I guess it would be FFNN, wouldn't it? Because I said FNN. No, I said FFN. But yeah, okay, Starry Vibes. So you were, I got what you were saying. I just, the acronym FNN, I don't think I've ever come across. But thank you for that. So for the definition of GAN, Yassine is posting generative adversarial networks. Okay, cool. So I'm going to take a small diversion here, guys. Because we are not going to learn about GANs today. I have that planned for next weekend. Or next Sunday, I should say. And the reason I say that is because I'm not sure if GANs are its own neural network as much as they are a neural network architecture. And I think that distinction is important. I would argue that it is an architecture, not a type of neural network. If you guys have done a little bit of work with GANs, you might understand what I mean by that. If you don't understand what I mean by that, that's okay. We're going to cover that much more in depth next week. But for today, for those of you that do know what GANs are, I would propose to you that they are not a type of neural network. So we actually won't be focusing on it today. Okay? And hey, I'm happy to be wrong on this. If you guys, I'm open to debate. If you guys want to tell me otherwise, feel free to do so in the chat, okay? So Ayush, our new friend Ayush says neural network frameworks is TensorFlow, PyTorch, Keras, and JAX. Okay. I'm familiar with the first three, obviously, but not JAX. So somebody wants to fill me in on JAX. Give me the elevator pitch on JAX, sir. I'd appreciate it. Denelson says, yes, there are different types of neural networks. There are models like CNN, RNN, LSTM, so on, can be most effective with data that are close to a time series, where CNN can work best with images. Okay, Denelson. So remember how I said that Yassine had a very interesting way of closing out his definition of these neural networks, right? So last week we talked a little bit about this, about how people say, oh, RNN, that's for time series. Well, no, it's for data that's it's 4-dimensional data, right? It just so happens that time series is data in a single dimension, right? Because you can say that the series matters and the ordering and the previous inputs can have an effect on future inputs, so on and so forth, right? So I'm encouraging you to think about it in terms of the dimensionality of the data rather than, oh, it's time series. Because the same thing for CNNs, right? CNNs, people always say, oh, that's what I use for my image processing. It's good for images. Well, no, It's good for dimensional data, but that's multiple dimensional data, right? Because it's not a single pixel in a picture, it's a pixel that's surrounded by other pixels, right? So, like, in layman's terms, those edges and those connections count, right? It's important that this pixel is above this pixel, but to the right of this pixel, and then also below this one, right? But that's not an image, that's multidimensional data, right? So that's where I'd like for you to think about it, Denelson. So again, look back at Yassine's answer, because we need to kind of keep that in mind, that all of the YouTube tutorials, the fake influencers, all, the idiot influencers, they always say, "Oh, use this for time series." Well, but that's kind of an ignorant statement, right? It's not that it's time series; it's that it's single dimensional data or multidimensional data, right? That's really kind of what we want to know. Because remember, the neural network, the algorithm, it doesn't know it's dealing with time series. It doesn't know it's dealing with an image, right? It's all math to that, right? So keep that in mind, guys. Single dimensional data versus multidimensional. Ayush, we're going to come back to your question, okay? Manoj says generative adversarial network is the workflow or architecture. Yeah, Manoj, I would agree with that. And again, guys, if you don't understand what Manoj means by that, that's okay. That's okay. You can still stay. But next week, we're going to talk a little bit more about that. Let me read ahead here a little bit. Okay, so Starry Vibes says 3. 3, is every grid search successful? No, it can get stuck in local minima. That's right. The local minima is one of the many problems a grid search can have. But what we really should remember is that not every grid search is successful. Not every set of experiments is successful. So if we go to our terminal window, some of you guys might remember this, right? We worked on this a couple of weeks ago, right? Hold on a second. That's not refreshing. Give me just a second. There we go. You guys might remember this. Who remembers this, right? Remember this terminal output? Remember how slow it was? We actually had to cut the session short because this was so long, and this didn't finish by the time we finished our session. And this is a terrible model, right? But it was a grid search. It was a lot of epochs. It was supposed to be a better architecture. I believe this is an RNN that we did, if I remember right. But wasn't successful, right? And not to get on a tangent here, but this is one of those things that I kind of have trouble with machine learning in general, or AI in the public eye and things like that, right? Everybody assumes that machine learning can solve everything, but that's not always the case. Machine learning models at the end of the day are still math formulas, right? It's all still numbers based. So that doesn't mean that every single attempt you do is going to be successful. So going back to Starry Vibe's answer, it can get stuck in a local minima, right? There can be other problems with it too. But not every grid search is successful, guys. Just because you run 1,000 experiments doesn't mean like you have to get a positive result. You have to be willing to say, we ran the experiments and we couldn't get there. Lots of companies are unwilling to do that. All right, let me go back to my deck here. All right, so Denelson says, when it comes to learning rate, there is no learning rate that will be effective. DS experiments to determine if their model needs to take big steps or small steps to find the minimum, nitty gritty. Yeah, Denelson. I like the way you put that. Thanks for that. And I think you're on the right track there. Thanks a lot for that. Yes. Yassine says, yes, I can see the argument for that. It's not manipulating the node calculations and processing method. It's just structuring the existing types of neural networks in a way to achieve a certain objective. Yeah, Yassine, I think you're talking about the multidimensionality of it all. But yeah, I mean, I like how you mentioned the node calculation, because again, guys, remember the neural networks are math representations of the brain. That doesn't mean it's thinking. It doesn't mean that like it's, you know, sentient or making decisions on its own. It's just picking the best result from what the math says, right? And we're going to see a little bit of that today. So remember, the model doesn't know what it's working on. The model just knows the numbers. That's it, right? Denelson says, grid search is a way for us to automate experiments of different configurations for hyperparameters so we can find a good enough model and then retrain the model and further tune it. Yeah, I like that, Denelson. That's a pretty good definition there. Denelson says, there are frameworks that we can use for neural networks. The two most popular are Keras and PyTorch. We use Keras and not PyTorch because we have families that love. Okay, so Ayush, our new friend Ayush, says, why do we never use PyTorch? Because of production challenges it has. Not sure about it, but curious to know more about why. So Ayush, I would like for you to encourage you to read Denelson's answer. PyTorch is only for people who didn't grow up with a father in the home. So if your father went out for cigarettes one day and never came back, Ayush, you're welcome to use PyTorch. That didn't happen to us, so we're going to choose to use Keras and other frameworks that, you know, make sense. But Ayush, the decision is ultimately up to you. But Denelson, thank you so much for showing that it's not your first rodeo. Denelson understood the assignment there. Yassine says that he was referring to GANs. Okay. Yeah. Okay, Yassine, sorry about that. Yeah, I see it now. And Yassine, you're 100% right. That the argument that I was making is that it's not a type of neural network, it's an architecture. And yeah, you're modifying the structure of it all to get to a desired result, right? And really to say a desired generated result, right? But yeah, Yassine, we're on the same page there with the GANs. Okay, cool. Are there any last answers or any last questions on this deck before we move on? Or excuse me, on this slide before we move on? Ayush says, what an analogy. Ayush, I do my best to teach you guys serious, right? But at the same time, you know, we can always have a little fun. And like I've always said, for full disclosure, I am one of the moderators on the Keras mailing list, so I am a little biased. I fully recognize my bias. But my parents aren't divorced. I didn't grow up in a broken home. What can I say? I like Keras. Ayush says, I love it. Well, thank you, Ayush. If you love that, then you're gonna fit right in. So just keep on coming back. All right, let's go to the next one. So we already had Starry Vibes mention feed-forward neural networks. And by the way, guys, I assume that most of you are already going to know what's on these slides. But for some reason, I just felt like I needed something where we actually state it so that we as the group can have a collective understanding of what we're talking about when we're talking about these feed-forwards or these RNNs, CNNs, and all that, right? So these are the general definitions or general guidelines that I'd like for you to keep in mind. So feed forward starts from your input layers and makes a pass through your output layers, and that's it, right? It doesn't go back and try to make changes and adjust and take information that it's learned and make adjustments to previous layers and all that. It just goes in one direction, feed forward, right? Pretty easy. All right, recurrent neural networks. It maintains a memory of previous inputs so that it can create a context for itself. You'll notice that I said, and I chose my words carefully here, tends to do well with time series data. But as I prefer to say, it's also sequential data with a single dimension, right? We're basically saying that order matters. The order in which I'm giving you the inputs matter. That's basically what you're saying with an RNN. It just so happens that time series also shares that quality that the order matters. But remember, the model doesn't know you're giving it time series data, right? So we got to think about it is that RNNs do well with sequential data in a single dimension, right? So keep that in mind, okay? And if you want to actually think about this a little bit further, what else is data where the order or the sequence matters? What else? Think about that. Let me know in the chat. What else is out there where sequence matters? And also keep in mind, I chose the tends to because again, there's no rule that says you have to do this. Too many of the idiot influencers out there are, oh, it's time series. Oh, we must use an RNN. You don't have to do anything. That's part of the experimentation of life, right? Experimentation of data science. Maybe a feed-forward neural network will work just fine. Or if we go back to our previous example, right? We did do an RNN on this data and it performed horribly. What are you going to do then? Just stop because, oh, well, it's time series. We have to use RNN. No, you don't. You can do whatever you want. Right? So keep that in mind. So for my previous question of what else is sequential data with a single dimension, Yassine says NLP. That's right. Text data, right? Text data is sequential. It matters where you put the words, right? You can't just output all the words of a sentence, even though every single word is correct and fits the sentence. The order in which they're in matters, right? So yeah, Yassine's right. Text data is sequential, arguably single-dimensional data, right? So I'm using it again to reinforce that sample. Don't get stuck on RNNs for a time series. It can be for anything you want it to be. It tends to do well on time series. It's best with single-dimensional data, but you never know. Right? Manoj says, agree with Yassine. Yeah, Yassine was right on that. Right? And by the way, guys, if you're feeling shy or don't always know the answer, feel free to do just as Manoj did and say, hey, I agree with so and so, or I disagree with so and so. That's okay. You don't have to give a long answer everything. But again, right? It's not that it does well for time series, it's that it does well on sequential single-dimensional data. And there's a lot of other sequential single-dimension data that you can come up with out there besides time series. Okay? All right, next one. Convolutional neural networks, or CNNs. So this also tries to create context, but it just does it with more inputs. So it assumes that whatever data you're giving it is part of a grid. So it wants to take all the edges into account. Right? So if single-dimensional sequential data is just on one plane, CNN says, well, wait a minute, you could have multiple planes. So I want to know not just what's beside it, but what's on top of it, what's the diagonals, what's on those edges. And it just so happens that that's also convenient for pixels, right? Pixels have edges. You can't just have a jumble of pixels. It matters that this pixel is above this one, below this one, to the left of this one, diagonal of that one. It's this color, whereas the one next to it is another, right? Like, it matters. So CNN takes that into account. But again, the neural network does not know any of that, so it does well with sequential data with multiple dimensions. That's really the takeaway there. And again, I'm sure that there are other examples for sequential data with multiple dimensions that go beyond pictures, right? There could be other things out there. All right, let's go to the next slide. I thought I'd bring this up because I thought this was kind of funny. But what is this trying to capture, guys? What makes this meme funny? Let me know what your takeaway is on this one. I'll give you guys a minute to think about it. Go ahead and tell me in the chat. Yassine says, if I can share an example we worked on to emphasize the idea that it's essentially about the dimensions. One time we used CNN to classify the problem type behind missing data in tables. Okay. Yeah, I could see that, Yassine. I could definitely see that. There could definitely be reasons why you'd want to do that, right? If you're trying to fill in or classify why you had missing data in a sequence, yeah, that would be very good, right? So thank you, Yassine. Appreciate that example. Fabrizio, welcome back. How are you, Fabrizio? Hope you're doing well. Fabrizio says, I think you need to feature engineer data before sending. If not, we cannot explore fully the patterns on the net. I think you need to feature engineer data before sending. If not, we can explore fully the patterns on the net. I'm going to assume you mean the patterns on the neural network. Fabrizio, I'm going to say that your statement doesn't hold for a lot of scenarios. Today we're going to focus on image data, and I would say that image data is one of those, right? You don't tend to have too much feature engineering on image data. You would also say the same for like audio data, right? Or signal processing. You actually kind of don't want to have a lot on those types of scenarios, right? So in some scenarios, I would agree with you, but you can still do a lot of learning and a lot of exploration without any feature engineering. I actually had this conversation with one of my clients recently. I'm giving him private NLP lessons, like private tutoring lessons. And one of the beauties about NLP is that like there's a lot of pre-processing that exists for NLP, but there's no rules that you have to use it. There's no rules whatsoever that you have to use it. You can do whatever you want with the pre-processing. I don't want to talk too much about the project, but I worked on a project where I wanted to keep emojis. Like I treated emojis as like text or as communication, right? Like you wouldn't say that for every project, but like there's no rule around that, right? So I understand the spirit of your point, Fabrizio, but that's not always the case. You can do a lot without any engineering, and in some cases you don't want to do any data engineering or feature engineering, right? So keep that in mind. Keep that in mind, guys. There's no rules when it comes to that. You can make that part of your experimentation. Like I've done NLP projects where you can say, I got these results by using this stemming approach, but I got these other results by using a different stemming approach, right? You can do that, but you can also do none of it if you wanted to, right? So it's all part of the flexibility of data science. Okay, so coming back to the meme that's on the screen, Michael says overfitting, I believe. Osama says overfitting. Denelson says, I believe that it will just remember the data and not train properly. I was a bit confused when it was posted. Yeah, so all of you are on the right track, right? And I think it's basically making fun of a lot of the AI companies where, they're claiming these ridiculous accuracy numbers and, test scores and things like that because they're just you're basically almost not inferring anything anymore, right? It's not an inference if it was part of your training data, right? So I thought this was funny because that's kind of like the approach a lot of the AI companies are doing, right? Where, well, we don't want to guess. We'll just try to get every single document out there and put it in there. Well, I mean, that kind of sort of can work until it doesn't, right? But I thought this was funny, so I thought I'd put that out there. All right, guys. So here's what I want to cover today. This is my coming up screen because this is what I want to work on today. We are going to work on an exercise for image recognition. We're going to use a modern framework, right? Up till now, we've been asking ChatGPT to give us raw code for our neural networks, and that's been a lot of fun. That's been very effective in helping us kind of take things apart and understand how they're working. But that's not how you'll be doing it in real life, right? In real life, you'll be adopting whatever neural network framework your team is already using, right? Most teams tend to adopt a single framework. We're going to use a CNN because we are going to be working with multidimensional data, not images. We are working with multidimensional data. We're also going to conduct a grid search. We're going to run some experiments, right? Basically with our grid search. We're also going to utilize a dropout rate. We haven't talked about a dropout rate. So in the chat, for extra credit, if you guys want, let me know. What's a dropout rate? What's a dropout rate? Let me know. We haven't discussed it at all. It just hasn't come up, but that's okay. It's going to come up today. The dropout rate is a really good example of something that is made easy by the modern frameworks. And we're also going to get away from like these binary type of decisions, because basically we've been like 1 or 0 has been our output, right? And we're going to see what it looks like to have multiple nodes in the output layer, because most neural networks that you'll work on, or a large number of them, aren't going to be binary yes or no, true false decisions. You're going to need multiple nodes in the output layer. And in some cases, you're going to have a lot of nodes in the output layer, right? So yeah, what do you guys think? Let me know if you know what a dropout rate is. Put that in the chat. And yeah, while you're thinking about that, let me focus on the dropout rate. So, because Starry Vibes has already given an answer. Starry Vibes says, I think it's used to reduce the complexity of the model. What do you guys think? Does anybody agree with Starry Vibes? Yassine says, what percentage of nodes to turn off in each layer? Okay, why would you want to do that? Why would you want to do that, Yassine? Denelson says, I have defined dropout rate as the proportion of nodes that my model will sleep to help with the complexity of the model. Okay. Denelson and Starry Vibes, maybe you guys can give me a definition for what you mean by complexity of the model, because that's where I'm stuck. I think you guys are generally on the right track, but you're losing me at complexity of the model. Osama says it's a regularization technique used in neural networks to prevent overfitting. Aha. Overfitting, right? I mean, that's pretty important, right? Just as we talked about on our previous meme, right? You don't want to get everything because then you're just overfitting, right? So how do we account for overfitting in our models? Like how are we going to prevent that ourselves? Right? Kind of an important discussion. Manoj says used to prevent overfitting. Yeah. See, so Starry Vibes and Denelson, that's kind of where you lost me, because I don't view it as complexity. I view it as the overfitting. Right? So Manoj says agree with Osama. Yeah, and Manoj, I think Osama would also agree with you. Yassine says, I want to do that to make sure the model does not unnecessarily focus on the very small details. Oh, Yassine, but what is small? What is small? The neural network doesn't know that, right? The neural network doesn't care. Yassine, buddy, I love you, but I'm not on board with that answer. Starry Vibe says high complexity is more flexible but risks overfitting. I'm not sure if I associate complexity with overfitting though, Starry Vibes. Complexity is going to affect your speed, the size, like the physical size of the neural networks, but overfitting, I don't know about that, Starry Vibes. Denelson says we use dropout rates so that we can help our model nodes don't grab all the information. Not information can be best. That can help us with reducing overfitting. Okay, so Denelson, I think you're putting forth a very reasonable definition there. So here's how I like to think about it, guys. Remember how we've talked about that a neural network is a mathematical representation of the human brain, right? That's the base definition we've established. So when I think of a dropout rate, I think of those times when you're just like, oh, wait, what was that? What was that person's name? Oh, wait, where did I go on vacation that one time? You forget things, right? We talked about those synapses and all the links in your brain. Sometimes those links don't work, right? Sometimes things just kind of get lost, right? So a dropout rate simulates that in training, right? Because it's a training hyperparameter, right? You really wouldn't need it at runtime. And that's where you simulate nodes dropping out, because that kind of simulates a little bit of a memory loss, a little bit of just like times when like your brain has to think about other, oh yeah, now I remember it, right? Has to find other patterns or other connections in your brain and in those connecting synapses to be able to say, oh yeah, now I know the answer, right? That's basically what a dropout rate is. It simulates that. It says, okay, this training round, I want to shut off X number of nodes, or proportion of nodes. And that way the network has to kind of retrain itself and say, oh, here's what I need to do to get to an answer, right? So that's really how I think about it. The benefit is that it prevents overfitting, right? Why? Well, because it has to find other ways to an answer, right? You're forcing it to adjust. You're forcing it to say, okay, yeah, well, in times when you don't know this, or in times when you get a bad answer here, make sure you find an answer by going over here, and here, right? So that's basically how I think about a dropout rate and the benefit of it. Because you are preventing that overfitting, because now when you present data, it's kind of sorted to a different neural network every time, because different nodes will be shut off, right? Same proportion of nodes, but that's kind of the point, to help you have different neural networks answering the same answer on the same data. Manoj says, I feel complexity can be addressed as high dimensionality, open to being wrong. Manoj, I want to credit you for saying open to being wrong. I think that's a very healthy attitude for a data scientist to have. So good for you, my friend. Complexity can be addressed as high dimensionality. Sure. High dimensional models tend to be complex. So I agree with that. But it's not the only source of complexity. Remember how we talked about the neural network architecture can be whatever you want it to be, right? There's different implications of your choices, right? If you need it to be a fast neural network, or it can be a little slower, or you're going to have a lot of hardware, you're going to have a little bit of hardware. There's implications to those choices. But complexity can also be addressed or created by the architecture that you choose, right? So I think you're on the right track overall there, Manoj. Fabrizio says the model becomes more resilient and flexible. The dropout rate is the fraction of neurons randomly set to 0 during each training step. Yeah, that's reasonable. Yeah, guys, and if it's very important how we express ourselves, right? So one of the things I always tell my clients or my beginners is always, it's not fractions, it's not percentage, it's proportion, right? If you want to sound like like a professional statistician or professional data scientist, we use proportion. So keep that in mind, guys. It's just one of those things that when I learned that and when I adopted it, it felt like it elevated your career, your status, right? We don't say fractions, we say proportion. Osama says turning off parts of neurons during each training iteration. Yeah, Osama. I think you're on the right track there, in line with all the other items. But again, guys, just remember, it's just another extension of simulating the human brain. The human brain is not perfect. You're going to forget things, right? But your brain doesn't say, "Oh, I forgot that. I'm never going to think about it again." Your brain finds other ways, other connections, right? Same thing. All right, guys. So number 4, I want to talk about real briefly. We're going to have multiple nodes in the output layer. Because if you remember before, we were using our XOR, right? We were using our XOR table as our data to be able to say, hey, this is the input and this is the desired output, right? 0, 1, 1, or 0. So that's basically a binary output. And we were only getting one probability, right? This probability here that tells you whether it was 0 or 1. So here, this is telling you it's 998. That means it's closer to 0. That's closer to 1, excuse me. So the likely answer is 1. Here it's 0.004, which is close to 0, which means that the likely answer is 0, right? But what happens when we go beyond ones and zeros? It's kind of important, right? So when would we need to do that? We are going to work on what is known. By the way, guys, I'm sorry if I'm mispronouncing this, but I've always referred to this as the MNIST data set. Maybe I'm wrong on that. If somebody wants to correct me on that, but I've always referred to it as MNIST. If you've never heard of this data set, it's basically a collection. Oh, actually, no, let me increase this. Sorry, guys. It's basically a collection of images. And those images are handwritten numbers. So what we're going to do is we're going to take, this is going to be our data, and we are going to create a neural network to determine an input picture and say, what number is this? Right? So, taking everything we know about neural networks and all that, how many nodes are going to be in our output layer? We want to keep an open mind to what our architecture is going to be and all that. But one of the first things you should establish in a neural network design is your output layer, right? Because that gives you an idea of the complexity and the time it's going to take you, all that stuff. Put it in the chat. How many nodes are in our output layer? All right. So Yassine, Starry Vibes, Denelson, Michael, everybody's coming up with 10. Okay, why? Denelson says 1 for each type of number. That's exactly right. Thank you, Denelson. That's exactly right, guys. So if that's not clear to you, we're basically saying we're going to have a neural network. And these are the possible results from that neural network. Or as Yassine says, we have 10 classes, right? Each one of these numbers represents a class. Right? So we have to assign a probability to each one of these classes based on what our neural network knows. So speaking of complexity, right? You, as the data scientist, should immediately be aware that, hey, this is going to be a little bit more complex than your average model, right? Because if you're going to have 10 outputs, that means you're going to have a fairly sizable model, right? Because, 10 outputs, you're unlikely to reach a good answer with only just a couple of layers. You're probably going to need multiple hidden layers. Each one of those layers, you generally want them to be bigger than the number of outputs. Maybe just as a starting point, we'll use 30 nodes. I mean, I'm making that up because any answer is valid, right? So right away, you should be knowing, oh, wait a minute, this is going to be a serious effort, right? Some of the biggest models that I've worked on, I think, have been up to like 46 or 48 different classes, right? Which is a lot, right? You know that you're going to be investing into a serious model when you're doing that. But I'm bringing this up because these are the types of like mental calculations that you can make just by talking to stakeholders, just by sitting in general meetings, right? You don't need to code everything out. You don't need to, um, run experiments. This is more about like just kind of like the experience side that you develop as a data scientist to say, wait a minute, there's a big difference between me developing something that has 3 or 4 classes versus 15 classes, right? I mean, think about what this looks like for the American, or rather the English alphabet. English alphabet has 26 letters. So now you're going to have 26 classes, right? So what does that look like? Well, that's a big network, right? So I'm encouraging you to kind of think about it in those terms, because this is how you can come up with like ballpark figures to know like, okay, wait a minute, that's going to be a pretty significant effort. I need to be careful here on the questions I'm asking and make sure I have enough data, because the more classes you have, generally speaking, the more data you need, so on and so forth, right? So keeping that in mind, we're going to be working on a neural network that most likely will be image data, which most likely, or we'll start with CNN. We're going to use a modern framework instead of raw code, and we know that our output layer needs 10 nodes. Okay? Are you guys with me so far? If anybody's lost, that's okay. Let me know in the chat. But otherwise, let's go ahead and start going into ChatGPT and start building out this sucker. All right. So give me just a second, guys. Let me bring up I guess we're ready for the web. Oh, wait, we are in the web interface. Okay. I think we are going to stay with O4 Mini. O4 Mini has given us pretty reasonable results so far. And I point that out, guys, because we've been using 4.0 a lot for our coding, but 4.04 Mini is not too bad. So let's just keep going. In this scenario, we're going to assume that ChatGPT knows about the MNIST data set. It's a fairly standard data set that's used by, a lot of people, a lot of training. So we'll just kind of start building our prompt from there, okay? So oh, you know what? Let me increase that. Sorry, guys. So we're going to specify that we want it in Python. We're going to specify that we want to use the data set, and that we want to start with a fairly simple example, and then we'll build it up. I believe that MNIST is already built into Keras because Keras does have some sample data built in. So we're going to go ahead and ask it to use it. Use the MNIST data as available in Keras. MNIST data set. So yeah, let's start here. I'm tempted to prompt it a little bit more, but we can make adjustments later on. But let's see what it gives us as a first pass. I was thinking because I wanted it to kind of maybe break out the training versus the prediction cycles, but let's see what it gives us. All right, so here's a simple Keras example. Okay, yeah, so it does have it. If you notice, it's making a call to Keras dataset MNIST. It's giving us our training and our testing data. Yep. It's going to use accuracy as the main metric. It's going to do 10 epochs. Okay. So this looks like a reasonable example. Let me go over here. We're going to start a brand new new sheet or new code, and we're going to call this NN4. We're going to put it in here. 54 lines. Wow, 54 lines is pretty good, guys. So this is a fairly simple example. I think ChatGPT did a good job of keeping things easy for us. So we're going to go this line by line just in case anybody is lost. But basically, here we are breaking out our training and our test set, right? You always want to have something that you're training on, and then you want to have your test that you're testing against, right? Here, it's going to go ahead and take and make those images flattened out into 28 pixels by 28 pixels. And that way it gives you a vector length of 784. And then it's going to go ahead and normalize the pixel values to 0 or 1. In other words, it's going to turn it into a black and white image, right? That's essentially what you're doing when you're saying, don't give me the color, just tell me if it's black or white. Or, you know, shading light or shading dark, and then turn it white or turn it dark. And then here we are going to go ahead and we're turning it to one hot encoded vectors. At line 20 is where the magic begins, right? Because in line 20 is actually where like the work happens. This is our input layer, and then these are our 3 hidden layers. That's what it's recommending. It's recommending 3 hidden layers. One of them is going to be 256, one of them is going to be 228, and then here in the output, I meant to say 2 hidden layers. The last one is the output layer. And the output layer, it knows that the number of classes it needs is 10. Yep, it established that up here. I don't know why it hard coded that. That's weird. It could have found that in via other ways. And then it's gonna assign an activation function to those final nodes, right? And with softmax, if you guys remember, softmax is what? Is softmax a step function, or is it more of a gradient function, like a sigmoid function? Let me know in the chat. What do you guys remember about softmax? Is softmax a step function or a sigmoid function? Excuse me. Let me know in the chat. And then the compile is what actually puts the entire neural network together. The compile is a Keras call, if you guys haven't seen that one before. And then these are our training parameters. The fit is the Keras method that actually does the training. Here's where we're putting in our epochs. We're putting in our validation split where we're saying withhold 10% of our records for validation. And then here is where it actually gives us the results. Right? So I think this is pretty good code ready for us to run. We don't have these though. We don't have NumPy or TensorFlow or Keras. So let me go back to ChatGPT and figure out the imports that we need. Or the pip installs, I should say. Pip install TensorFlow, that should be it. Okay, so that's pretty good. All right, let's go ahead and do that. What the heck? It couldn't find one. Okay, that was weird. Let me upgrade my pip just in case. What is going on? I think I could just probably do Keras instead. Let me just do that instead. ChatGPT might have made a mistake in telling us to install TensorFlow. Let me know what you guys think about that. That was a weird error. But let's go ahead and try to run this. So Python nn4.py. No module name TensorFlow. Okay. Okay, that's weird. Fabrizio says maybe the name is different. Yeah, I think you're right. So let me show ChatGPT the error. Oh, right. The Mac OS is might be part of it. Or not. Wow. I feel like we had this error before, chat. And I want to say it was related to the version numbers. Does anybody remember that? JR, I think you're new here. Welcome. JR says virtual environment. No, well, I mean, it is a virtual environment, but I'm using Conda. Guys, maybe some of you remember this, because I know we've used Keras before. I think we had to downgrade our Python version, didn't we? Wasn't it something like that, guys? Does anybody remember that? I want to say it was related to our Python version. This is weird. Let me follow everything that ChatGPT says. Okay, setup tools wheels. Now we can try Mac OS again. Nope. Metal is also not going to go. So let's show that to ChatGPT again. Yeah, it supports 3.11. Okay. Yeah, that was the answer last time, chat. I tend to lean towards the latest version of Python, which doesn't always agree with Keras, which is kind of weird, right? So we're gonna have to downgrade uh our environments. So I just want to be reminded of what that command is. Yeah, conda create and then yep, okay. So let's go ahead and fix that in the terminal. So we're gonna say we're gonna deactivate this. We're gonna create a new one with Python 311. We're gonna name it NN2. So that looks good. All right, cool. So now we're gonna go to conda, activate NN2, and we're gonna go to the initial recommendation, which was pip install TensorFlow. Okay, so that's gonna work. So guys, I'm not in agreement with it, but apparently, the libraries don't always support the latest Python version. So if you're not aware of what just happened, I created my environment in Python 3.13, which I think is still the latest release. But that was causing problems with the latest versions of Keras and TensorFlow. So we had to downgrade our Python by creating a brand new environment, right? Separating that out from our other work, create a new version in Python 3.11. And now the TensorFlow install works just fine. So now, if we go back and we run that same Python file, the code that ChatGPT gave us, this should work here. So it looks like this is going to go. Okay, so there we go. So now we're running through our epochs. So if you guys have never seen it before, everything you're seeing right now with the epoch list and the steps and the accuracy and all that, that is all a function of Keras, right? This is kind of like the value add that you're getting from working with an environment, a modern neural network framework, where it will give it to you and say, okay, well here, now let me take over. You told me what architecture you wanted for your neural network. And now I'll take over and I'll do all the math, all the different changes and arrangements and all that. And it'll do it internally within the library, right? Because remember, if we go back here, we can see that our code is only like 50 lines. This was an optional one, right? But it was only like 46 lines for the entire, like the base of the code, right? So pretty reasonable, right? Pretty reasonable to bring in that framework and have to deal with a little bit of setup and a little bit of overhead, but it really just kind of helps you instantly get some more information and data out of it. Uh, Casual Economist says, I'm late. Can we start all over? Welcome, Casual Economist. Yes, of course we can start all over. So, Casual Economist, today we started our stream by everybody giving a 10-minute presentation about themselves. So, yeah, if we want to start over, go ahead and start, Casual Economist. The floor is yours. Yassine says, is it supposed to be showing the training cycle? I don't know if it's just me, but I can't see it. Yassine, yes, it is supposed to be showing a training cycle. Did it not do that? I think it did, right? Or wait a minute, did I? Gosh, oh man. You know, guys, I'm sorry. I don't know why it's doing that. My OBS keeps dropping my screen capture, right? Because I have like a second monitor that I use for all of my work. Yassine says now it does. Yeah. Sorry, guys. I don't know why that refresh rate is failing, but it doesn't seem to restart the capture. So I have to do it manually, which is really annoying. But yeah, thank you for that, guys. But yeah, this is what it looks like, guys. So everything you're seeing on your screen right now is a convenience of working with Keras, right? Because this is all Keras output. We didn't program any of that. This is what's baked into the library, right? So the library is telling us, hey, I ran this epoch. I used 422 batches. Here's the accuracy. Here's how I improve, so on and so forth, right? So let me know if anything on this screen is catching your eye. I haven't looked at it yet. I'll take a quick look here. Osama says, if one framework is compatible with Python 3.11 and another requires 3.13, what approach should we take to manage both? It depends. It depends, Osama. Are you talking within the same project or within the same server or whatnot? Because virtual environments should be able to handle what you're talking about, assuming separate projects. Yeah. Otherwise, you'd have to get more into project-specific needs and figure out, what needs to actually talk to what, and go from there. But virtual environments, Conda, all of that should help you with that problem, Osama. Common problem, by the way. Casual Economist says, I was born on a farm. It was cold and rainy night from what I remember. Okay, keep going. You've taken up about 20 seconds. So you got a long way to get to 10 minutes there, my friend. All right. So let me take a quick look. Does anybody want to point out anything that they're seeing on here? What do you guys think? Is this a good model, bad model? Do we need to try again? What do you guys think? What is your general impression? If you're lost, that's okay too, right? Let me know. But what do you guys think? Give me your impressions. What's your interpretation, right? Results interpretation, super important part of being a data scientist, right? So I've already made my interpretation, but you guys tell me, what do you guys think? Yassine says loss is good, accuracy is good, both for training and validation test sets. Starry Vibe says, I think it's a good model. Starry Vibes, why do you say that? Yassine says, we didn't need that many epochs, that's for sure. Yep, 10 epochs, pretty fast, pretty fast. What else do you guys think? Anybody else? What do you guys think? Is good model, bad model? Are we on the right track, the wrong track? Do we need to redo everything? What do you guys think? Fabrizio says, how is accuracy and loss being calculated? How is validation, accuracy, and value loss being calculated? Is it using MSC or cross entropy? Is accuracy calculated as an F1 score? It is using cross entropy, right? We can see that in the code. And accuracy is not being calculated as an F1 score. I believe the default for Keras is just to do it straight up accuracy. Manoj agrees with Yassine. Osama says, I believe it's a good model. Michael says, please explain. Michael, which portion do you want to explain? I mean, if it's the whole output, that's okay, right? But let me know which portion you're referring to for the explanation, okay? Because there is to Michael's credit, there is a lot happening on this screen, right? So that's why I'm kind of challenging you, all of you guys who say it's a good model. Tell me why. What on this screen is kind of, making you conclude that, right? And like I said, guys, results interpretation, model interpretation is extremely important in your career, right? So I'm gonna kind of push you guys a little bit. Why are you guys saying that? Why is it a good model? Or if you're maybe just a little bit confused or whatnot, like Michael, feel free to say that too and say, hey, I need a little bit more in-depth explanation. What do you guys think? Starry Vibe says, I think Epoch 9 does better than 10. Look at the validation loss in line 9 and 10. Okay. I love that observation. Denelson says, it does look good. Could we get back to the recomposition scores and a confusion matrix? Okay. Michael says he wants to explain the whole output. Thanks. Okay. All right. Yeah. So all very reasonable comments here, guys. So let's try to address Michael. And in that process, I'm going to also try to address some of the other comments that people are making, okay? Give me, you know what, guys, just to make things a little bit easy. I'm going to rerun everything we just did. I want to clear out the screen just so that we're clear that everything on this screen right now is generated by Keras. And we're getting similar results, so I think we're going to be okay here. Although I might have just tanked Starry Vibe's previous observation, but it was still valid, so I'm still going to focus on it. Yeah, okay. Okay, so first of all, the first understanding we should all have is that everything here was generated by Keras. We did not write any of the code to generate, to explicitly generate this output. That is a function of the library. That is why you want to use a modern framework, because all of that is baked into the library itself, right? All we did was say, hey, we think this is an architecture of a neural network that we think will work. Why don't you go ahead and try that, right? That's all we did, right? Because our biggest contribution is this section right here, the build the model section, right? This is basically like the only part that's really not done for us, right? Everything else is kind of sort of like predefined, right? Because we know we can't change our data. We wanted to use the min set. We flattened out the data, fairly standard pre-processing. There's going to be 10 classes because there's 10 numbers. Like, we're not making any decisions here, right? Here, we're making decisions. Here is where we're saying, okay, well, here, we want this layer, we want this activation function, so on and so forth, right? And that's basically all we've defined, but and the number of epochs, right? We defined that, right? But that's it. Everything else here was created by Keras. Okay, so that's the first thing we want to understand. 10 epochs. We define that, right? And we've seen epochs in our other parts. And basically, as we've defined it, it's basically giving the algorithm a new chance to start all over again, right? An epoch is day one in school all over again. So we've given it 10 opportunities to train itself, essentially. Within each one of those epochs, it will go through the data set and try to come up with the best model, and then take that model forward into the next epoch and learn a little bit more, so on and so forth. So in theory, more epochs, more better, gives it more of an opportunity to learn from its past mistakes, right? All right, so that explains why we have these epochs, okay? This is telling us a little bit about the performance, right? How long each epoch took, which for these models is not critical because they train pretty quickly, but as you get into larger, more complex models, that's gonna matter, right? All right, so now we have 4 columns that look very similar, right? So Michael, I want you to think about these as this accuracy and loss is one conjoined column, and this accuracy and loss is another conjoined column. And what we're basically saying is that this accuracy and this loss applies to our test data. Okay? And then we're saying that this accuracy and this loss applies to our validation data. Because if you remember, we chose a certain proportion of our records should be held out for validation testing, right? We designated that. We designated that as 10%. So this is what happens when we use our test data, and this is what happens when we use our validation data. And validation data, your validation numbers, are technically more important. I hesitate to say, but they should have more of an emphasis, because this is data that your training cycles never saw. They were intentionally held out so that this is brand new data to your model. So in theory, your validation data is kind of like your best reflection of your metrics, because it kind of simulates what you're going to do in the real world, right? When you actually go to use this. So that's basically what we're doing here, right? So think of these as 2 columns of 2, right? This accuracy and loss is important, and then this accuracy and loss is important. So your eye should be drawn to this one, because this is your last epoch, and these are the validation numbers for accuracy and loss. And as we've discussed before, accuracy, more higher, more better. Validation loss, more lower, more better. Anytime you start crossing into the 0.0, you're on the right track. And if you remember, in some of our previous classes, we've gotten down to 4 zeros, right? Where it's like 0.0000 something, right? The lower you can get to the loss, the better, generally speaking. So Michael, I hope that helps break it out for you, but that's essentially what's happening here. This tells us how the model is doing. Now, if we look at this line here, this line is very similar to the comment that Starry Vibes made about the earlier model, where it is possible where you will have epochs that are actually better along the way. Because remember, guys, just because you give it more epochs, you're not guaranteed a better result. You know, that's a fundamental mistake that a lot of people make. Just because you try more in machine learning doesn't mean it's going to be better, right? So there are going to be models along the way, as Starry Vibes made the observation previously, where these numbers are actually not too bad. They're actually pretty good. I mean, that's a pretty high accuracy, right? 9788 is bigger than all but one of these, right? And the validation loss matches what our 10th epoch was, right? So those are the types of things that your eye should kind of be drawn to. Okay? But overall, people are saying that this is a good model, and yeah, there's reasons to believe that this model can fit our needs, right? There's reasons to believe that this model is on the right track and will get us to an answer, right? Denelson wanted to see this more of in a traditional confusion matrix, which is what we've done in the past. So I agree with that. We're going to do that. But let me look at some of these comments. So Yassine says, I think it's a good model, good results, loss is small, validation loss as well. They are not so close, but not too far to worry, I guess. Yeah, I agree with that, Yassine. I mean, they are not equal, sure. Fabrizio says, the accuracy is being calculated, accuracy, number of correct predictions, predictions, that's not, softmax front. Yeah, sure, Fabrizio, I'm on board with that. Michael says, okay, thanks, it's clear now. Okay, good, Michael, thanks for that. A good question, Michael. All right, so let's go back to our ChatGPT and let's get a confusion matrix. I think that's a good idea. And you know what? We'll ask for it as a plot, right? We'll ask it to kind of show it to us in a graphical manner. Graphical manner? Yeah, you can say it. So I expect that the general code it's going to show us is going to be basically the same. It's just going to have like additional outputs, right? Okay, so we're going to copy that. Let's bring it over. We're going to call this NN5 just in case it made too many weird changes, right? 52 lines. Okay, it gave the confusion matrix. Oh, shoot, I copied it too early. It was still going. Okay. Predicted label, true label. It's going to show us the plot. Okay. It looks to be the same code. But it looks like we're going to need another pip install. Let me get those real quick. scikit-learn, matplotlib. Let me just get this. We're going to install these real quick, guys. All right, that should be good. And now we are ready to run NN5. All right, so we're going to see the same output basically, slightly different numbers. And then we're going to see the plot appear on our screen. Okay. And here's the plot it gave us. What do you guys think? What's your interpretation now? Let me know what you guys think. Anybody have any thoughts on this one? Denelson says, I think it looks great. So yeah, I'm gonna kind of keep that, and I'm still gonna kind of, well, let me go this way, so we can see the accuracy in the loss numbers. Give me just a second. Let me bring it down like this. So here's our accuracy and our loss numbers. So Michael, if you want to kind of narrow down your focus, this is a good way to think about just the last two columns, right? So yeah, I think Denelson's right. It looks pretty good, right? The chart looks pretty good. It's telling us it's making very, very few errors, and the numbers say that, right? A 0.9815 accuracy is pretty high, right? That's like maybe on this size of a data set, that's like 1 error, 2 errors, right? The loss is also pretty good. We had a loss. This one caught my eye. We had a loss of 699, which we didn't have any sixes in our previous run, right? So this run is actually pretty good, right? To have that loss is pretty good. Yassine says, not one false prediction, I guess. First thought is bad confusion matrix because, well, it's confusing. Not showing numerical result. That's funny. That's funny. And you're right, Yassine. I think that ChatGPT could have picked a better way to do that, right? Like the color gradient, I'm not really on board with. It's kind of funny, right? But I totally agree. Class for digit 1 is being classified the best. Oh, yeah, that's a good observation, Denelson. I'm on board with that. Fabrizio says, what does the colors mean on the confusion matrix? The diagonal is a perfect match. So the purple means that there were no mismatches there, Fabrizio, is what it means. That's the way you should be interpreting that, right? And Denelson is making the observation about 1 because it's the brightest number, or brightest on that gradient scale, right? But yeah, I mean, to Yassine's point, it's not really it's not I don't want to call it a poor visualization, but ChatGPT could have done better on it. Yassine says, I don't think the class or digit 1 is being classified the best. Okay, why do you say that, Yassine? Because I can see how Denelson drew that conclusion. It's just because it's the most existing case. Maybe. You know what? Let's ask ChatGPT to modify that, because I think we can all agree that this isn't the best visualization. It's an okay visualization, but not really ideal. Fabrizio says, so we don't have any colors like green, for example, on the purple side. It means it's not mislabeling. And the number 5 is the less accurate, let's say. Number 5, let's say. Yes, Fabrizio. Yeah, you're correct on both of those counts. I think you're drawing 2 valid conclusions there. That's right. But look, maybe most of us here are, we're not visual learners, right? Like the slow blinkers out there. Maybe we need something a little bit more quantitative. So let's ask ChatGPT to do that. But you know what, guys? I'm glad it kind of did that, because this is part of prompting, right? AI is not perfect. AI is only as good as you prompt it. Maybe we should have been more clear on the initial request, right? Maybe that's our fault, right? So we're gonna, you iterate just like anything else. You say, oh, that looks good, but let's do this. This is what I really meant when I said this, right? This is totally natural for us to go through this. All right. So we're going to copy that, and it says that each cell shows its raw count, which is maybe what we should have specified to begin with, right? So let me do that, and we're going to go ahead and replace this. I think we can replace this just fine. And let's go ahead and run it. Okay, so while we're waiting, Yassine says, if the color is based on the number of correct predictions, you can get a big number just by having it exist more in the validation data set, meaning it's unbalanced. Maybe, Yassine. I don't think that the validation set is that big to make that kind of difference. All right, guys. Okay, so technically speaking, ChatGPT did do what we wanted to, but the colors are awful. Oh my gosh. Okay, guys, that is terrible. We're not even going to try this. We're not even going to try this. What is the prompt we can fix here? We can say, okay, let's see if we can get rid of those purples. Purple on black is a terrible combination. But hey, you know what, guys? Another great example when people say, oh, AI thinks on its own and we're going to reach generalized intelligence. No, we're not. It just showed us a plot with black on purple. That is not intelligence, right? Oh, why are you... No, don't just import the plot. Do the whole thing. Oh, don't do that. All right, so it's going to show us the whole thing now. We asked it to remove the gradient. Let's do this. Let's do this. And then we're going to rerun it, and we're going to see where we end up. All right, so we're going to rerun this. 0.0660. That is the lowest validation loss that we've seen. All right. All right, guys. Oh, gosh. Now it changed the axis. Oh, gosh. All right, guys. So here's our confusion matrix. No color gradients. Counts only. Does anybody want to make any observations on this? That's about as big as I can make it, guys. Give me some observations that what's catching your eye here, guys? So Yassine, I see your latest message. So Yassine, here's an opportunity for you to kind of correct that, right? What do you think? All right, anybody want to volunteer their suggestions for this? What do you guys think? Anything jumping out at anybody? I'm trying to draw my own conclusions. And if you don't know how to interpret this, that's okay. You know, we'll get to that. But I'm just curious to see if anybody wants to jump in. Yassine says, I think the model does confuse certain numbers with each other. Okay, well, give me an example, Yassine. What makes you say that? Especially with numbers like 2 and 5. 2 and 5. Yeah, maybe a scene, but I'm seeing more in 3 and 4, right? 8 and 3. Yeah, I definitely agree with 3. 8, I don't think so. I think 8 looks fairly reasonable. The other one that's catching my eye is 1. How are there 3 instances where a 6 looks like a 1? That's kind of weird, right? Because I agree with you, right? The whole point of this confusion matrix is to find the ones that are being confused. But why would a 1 be confused for a 6? Right? I definitely agree with 3, Yassine. So guys, this is jumping out at me, right? Here, this value of 10. If you guys are confused on what's going on, what this is saying is that there were 10 instances where a 5, a value of 5, was confused for a 3. Right? That's what, because the y-axis is our true label, or what the number actually was. And the bottom axis, the x-axis, is what the model thought it was. So this line here, this value of 10 right here, says that there were 10 instances of somebody writing a 5, and the algorithm said, oh no, that's a 3. So that's a mistake, right? But then that's why this value is so high over here, because there were 867 instances where a 5 was written, and the algorithm predicted a 5. Right? That's how you should be interpreting this confusion matrix. So Manoj is saying 3 and 8. Yeah, Manoj, I think you're on the right track with 8. So guys, if we look over here at this number of 14, that means that there were 14 instances where somebody actually wrote an 8, but the algorithm said, oh, that's a 3. Right? That's how we should be interpreting that. Um, 4 looks fairly reasonable, Manoj. 4 and 9 is only, that's only 8 instances, right? So coming back to Yassine's previous statement, there were 1,121 instances where somebody wrote a 1 and it actually was a 1. So, Yassine, if that was part of your argument that it's just because it's a lot of numbers, I guess I can kind of see that, right? Because on the color gradient, it was by count. So, yes, I think if that was your point, then I think I would agree with that. I don't know if that was your intended point or not. But yes, this does kind of bring up a case a little bit of unbalanced data. It's not the worst unbalanced data set I've seen because they're all reasonably close to each other. But yeah, that is something you should take into account, right? Do you have, the more classes you have, the more data you need overall, because the more examples of each classification you're going to need, right? These are all hovering in the 900 to 1,000 range to the 1,100 range, right? They're all within 200 of each other. Guess what, guys? It's not always going to be like that. This I would call, compared to some of the stuff I've worked on, this is a very balanced data set, right? So I think that was part of Yassine's point, and that does come into play when you do have wildly unbalanced data sets. So this is a small example of that. So Yassine, let me know in the chat. But if that was your point, I see where you're going with it. Yassine says, yes, that's what I meant. Yeah. Yeah, so I agree with Yassine with the caveat that this is not a horribly unbalanced data set. I mean, you'll work on some data sets that are just like nightmares to work with because of there'll be so many classes and you'll always have that subset of classes that you have trouble coming up with examples on, right? But that's just the way it goes sometimes. Okay, anybody else before we get rid of this and move on? But what do you guys think? I mean, overall, it's not a terrible model, right? It's really not that bad. But here's the thing, guys, right? This might also be an example of a model where even though you're at 98% accuracy, it may not be enough, right? You may need to be much more accurate on that. Think about that. What if this algorithm was powering something where you were reading like dollar values or monetary values? Kind of makes a difference whether the algorithm thinks something is a 3 or an 8, right? Like that has serious implications, right? So in the chat, tell me, and I'm going to go over here. What can we do to improve our model? Here's our model, right? This is kind of like the core of the model right here. But then again, we also have other things, right? We have epochs and things like that. What do you guys want to try to help us? Anybody want to give suggestions? Denelson says, it is more clear now with the numbers to see where our model might need further tuning. Yeah, Denelson, it does help to know that, but we also can't always like fine tune, right? Like there's nothing for us to go into and say, oh yes, I just need to adjust this and my problems with the 8 and the 3 are going to go away, right? You can seek out more data. Maybe you can use it to guide you like what classification you need more examples of, but more data isn't always possible, right? So yes, it helps Danielson, but it doesn't necessarily like give you the answer either. It tells you what to go fix, not necessarily how to fix it or a viable fix. But let's focus on what we can do, right? Because there's always other things that we can be doing, right? So in the chat, what else can we be doing? I mean, we wrote this code, right? We should be able to adjust it. Denelson says we can try balancing our data set and apply a dropout rate. Justine says we can add another layer. I think dropout rate's already accounted for, isn't it? Maybe not. It is not. I think that is part of our compilation or the fit. I can't remember where we apply a dropout rate. I think it might actually be in the fit. Yassine says, or increase nodes and number of layers. Yeah. So guys, this should be a fairly straightforward question for all of you that have been attending. I definitely like Yassine's suggestion of we can either add more layers or we can increase the nodes of those layers. What is the trade-off that we are making in that decision? Are there any trade-offs that we need to be aware of in making that decision? What do you guys think? Let me know in the chat. What do you guys think? Denelson says more calculations with both additions and more time needed for the calculations, and increase in memory storage needed for all the calculations. Yeah, basically more models, or excuse me, more calculations, more processing, right? Or earlier, Starry Vibes and a couple of the people mentioned complexity. Adding more layers and adding more nodes increases the complexity, right? So that complexity comes at a cost of more processing power. That may be okay depending on your use case, or it may not. Are you running this on NVIDIA GPUs, or are you running it on a small Raspberry Pi? Two completely different considerations, right? Are you running it on a mobile app, or are you running it on a software as a service app, right? Where it will be hosted like on a server, right? So Yassine says, yes, we are risking increasing the model size and computational current. Yeah, exactly. But it's still a good idea, right? So let's try it. Let's try. What if we kept here? So, this is just me and my eye, right? Feel free to draw this out. But my eye, I can see that we have a 256 layer, a 128 layer. So it's kind of like a downward cone. So why don't we keep that going and go into a 64 node layer, right? So now our neural network is all these inputs. What is it? 784 down to 256 to 128 to 64. There's no rhyme or reason to that. I'm just kind of keeping with the pattern. It can be whatever we want, but that's the experimentation side, right? If I can't give you a rationale for 64, that means I can't give you a rationale for not using it, right? So that means you can use it because it's an experiment, right? So I'm going to try it. So we're basically added a new layer of 64 nodes, all right? And guys, here's where we're being data scientists, because what do we just do? We created a change and we just rerun, right? We just keep going. Okay, so it finished there. Here's our accuracy. Here's our validation accuracy, our loss, and here's our chart. What do you guys think? And just so we're clear on this, just to kind of state the obvious, but in case there's people out there who don't want to speak up, our entire goal is to lower these numbers across the board, right? Ideally, every number outside of this diagonal would be a 0, because that means there's no mistakes being made, right? So if we pretend that this is a financial application where it's very important to recognize numbers accurately, you really wouldn't want too many numbers outside of this, right? So what do you guys think? Anybody want to tell me about these results or anything else? Osama says, I think no model improvement. Yeah, that's possible, right? That's possible. Anybody else? Or you can just agree with Osama or something. Yassine says, I think it's better now. It only confuses the number 9 with 4. Yep, I saw that, Yassine. And Yassine's making a really good observation there. This number jumped out at me because it's the only double-digit number, right? So I want to focus on that because here's the thing, guys. Osama is not incorrect that it's not a better model because the accuracy is about the same. It's actually a little bit lower, right? This accuracy is 9808. Our previous model was 9815. Right? So technically speaking, Osama is correct. There's no improvement there. But here, Manoj is saying there is an improvement slightly. And I would tell you guys that neither one of these guys is incorrect. Because what I'm seeing is less double-digit numbers. Because if you remember, we had like a 10 here, an 11 over here, a 14 over here. So what we've really done is it's generally the same model, like accuracy-wise, right? Like numbers-wise, metrics-wise. But it's behaving completely differently because what it's done is it's spread out the errors. Because where there might have been a 14 here, maybe there were more zeros over here, but now those zeros became 1s or 3s, right? And that's why the overall accuracies are kind of close to each other. And to the eye, it can be like, oh, well, look, it's good to have 0 here, 0 here, 0, a 2 here, a 2 here, a 3 here, right? But all you've really done is kind of like reshifted the errors across the planes, right? Or across the different types of errors you can make, right? Because, another way to look at this confusion matrix is there's really just one way to go right. And it's this diagonal, right? This diagonal is like the way, right? And everything else is wrong. So there's a lot of different ways for you to spread that out, right? There's a lot more wrong capabilities than there are right capabilities, right? So I would say that both Manoj and Osama are correct. The model is very little to no improvement, but it does look like it improved. But really all you've done is kind of spread out the errors. And Yassine is correct. This one should jump out at us because it's also the only double-digit number. There's nobody else who's making double-digit, or no other category that's making double-digit mistakes, right? So this is a pretty good example of something where it's kind of sort of a wash in terms of your experiment. Different behavior, but you haven't really moved forward. Right? All right, so how about this, guys? Where do I go here? Tell me about the architecture and tell me about the processing time with the change I just made. What do you guys think? Tell me about the architecture, and how do you expect that this neural network's going to behave when we run it? What do you guys think? Yassine says 3 equally sized layers increase complexity and processing needed. Yeah. We no longer have a cone, right? This is no longer a cone. This is all this is all 3 layers being flat across instead of being like a cone shaped like a cone, right? How do I do a cone with my hands like a cone, right? So this is a lot more nodes, right? So yeah, slow processing, right? This is not going to be a fast runner. Should we expect better accuracy? Yeah. We're doing a lot more calculations, aren't we? Right? Okay, that ran. So one of the things I want to also mention to you guys, right? This is also, now that we're doing more and more experiments, this is also where we can talk about baseline models. So right now, we are at a baseline of a validation accuracy of 9815, right? So when we're talking about baselines, this is where we're talking about like the baselines, the champion models, so on and so forth. We can basically say, look, we know how to get to 9815. So if you show us something less than that, we're not interested. That's essentially kind of like what you're doing, right? You should say, this is our current baseline, our gold standard, and we're looking to beat that. So here, when we come up with 9787, we're already just a little bit suspicious, right? Because now we can say, okay, that's great, but we know how to beat that, right? We know how to be better than that. All right, so we're at 9787, and here's the confusion matrix. What do you guys think? Give me your observations here. I know most of us are going to be looking at this one now, 9 and 4. What happened to 9 and 4? What else does anybody want to observe? Numbers wise, you're really not that far, right? 9787 is not that much different from 9815, right? That's what? That's less than 0.005 of difference, right? Okay, yeah. Manoj says many double digits this time. Yeah, that's exactly right, Manoj. Remember how I said that? How we had previously kind of spread out the errors? In this model, we've kind of reconcentrated them, right? Because we have a 10, we have an 11, we have a 13. These all used to be just single digits, right? We have another 10 up here. Where else did I see one? I think it was this 11 that I saw that I'm mentioning twice. But we went from a spread out errors to more concentrated errors, but generally the same model, right? Right? Yassine says it's worse, more cases of confusion. Not necessarily more, Yassine. It's a different spread. Because remember, accuracy wise, we're within 0.005 of our baseline. So it's more about the concentration of them. Osama says 3 and 5. So 3 and 5 is now 10. That was not 10 in our previous model, guys. Right? So yeah, that's a concern, right? That we've kind of shifted those errors around, right? But it's essentially like on the macro metrics, it's kind of like the same-ish, right? So more nodes, not always more better, right? So let's do this. let's do, oh, what do you guys think about this? What am I doing? What does this look like? What are you expecting? Let me know in the chat. What do you guys think? What's going to happen here, guys? Osama says increasing model size. Yep, absolutely. We're back to the cone, aren't we? Right? But this is me saying, hey, look, maybe ChatGPT was on the right track with a cone. We just need a bigger cone because our first layer, or our first hidden layer, was 256. Maybe that was too much of a drop from 784 to 256. Maybe we need to go to 512, right? And then maybe we need to have a smaller on the downs on the far end, right? Let's go to 32. Let's see what that does. Yassine says bigger model and narrow architecture. Yeah, it's a narrow cone for sure, right? For sure, right? Let's see what this does. Not going to be a fast one, right? Not going to be a fast model here. Oh, wow. These numbers are terrible to start off. These are terrible. Okay. Okay. What do you guys think? 9817. Here's our results. What do you guys think? Let me know what's catching your eye. I already have a couple of conclusions. What do you guys think? Give me your conclusions on what you're seeing and what do you think we should do about it. Osama says no improvement detected. Are you sure about that, my friend? I don't know, Osama. Technically, you can't say that because we did beat our baseline. Not by much, but we did beat the baseline, Osama. So technically, you can't say that. And I think there's a couple things on this chart that should be catching your eye, too. What do you guys think? Anybody else want to give their view there? And then what else could we try? Because remember, guys, you can't always just increase the nodes and increase the network, right? Few double digits improved and spread of error. Yeah, Manoj. So what's catching my eye is over here, 16, 13, 16, and 12. All of the errors are basically concentrated in these four numbers, right? Like, look at that. Like, nobody else is even over like a 5. If you were to remove 7, 8, and 9, you'd have a near perfect model, right? Yeah, Yassine, that's funny, Yassine. Your message popped up just as I said it. Yeah, right? 7, 8, 9 is basically where all the errors are. Even 9. 9 has what, 28 different errors. 9 alone would remove 28 different errors, right? So this is actually well, we can say it's an improved model, right? We did beat our baseline. Is it a good model? No, because you're still failing on particular classes, right? But but again, guys, the takeaway here is how different the results can be. The spread of those errors can be completely different based on just small changes, right? Because now we have a highly concentrated set of errors. I want you to look at what Karas gave us. What is the next item? Excuse me. What is the next experiment that we should run? Remember, these have all been experiments, right? You and I have been living data science right now because we've been experimenting and walking through these different changes. What's the next experiment, guys? Give it to me. What's the next experiment? Give me the next experiment and give me your rationale for it. JR says 256, 256, 128, 64. Okay. Anybody else? Denelson says, what if we reverse the code? Okay. Um, okay. So Yassine has exactly the answer that I thought about. Increase epochs for the model. See if its full potential seems to improve over epochs. Yeah. Look at the way the model was progressing, guys. This is another way for you to interpret results. Are you on an upswing or downswing, basically, right? Did you give your model enough time to learn from its mistakes? To me, to my eye, this says, hey, another 20, 30 epochs could really benefit this model. We were on an upswing, right? The model was still kind of finding its way. Maybe it just didn't spend enough time learning 7, 8, 9, but given another 20 epochs, it'll get to 7, 8, 9, right? Not guaranteed, but it's like a reasonable assumption, right? What did we just do? We just created a hypothesis, right? Based on the data, the model was kind of on an upswing. We know it's not good. We know it needs more attention on 7, 8, 9, but let's see what additional time will do for that, right? So yeah, I think Yassine is correct on this. This is a really good instance of, hey, this just needs more epochs. Denelson says learning rate can also be tested. Yes, Denelson, you're absolutely right. We haven't done enough on the learning rate. So right now, we don't want to change too many things, right? Interaction factors, interactivity factors, and all that. We have to keep that in mind. But let's just add more epochs, guys. I think more epochs, obviously nothing is guaranteed, as we've always talked about, but there is reason to believe that more epochs is going to help us here. So epochs is here. Let's give it another 20 epochs. Let's go to 30. Let's go to 30 epochs. I mean, I think it's a reasonable expectation to say that we are now at 9817, and this next run should give us a higher baseline than that. That's a totally reasonable hypothesis for us to have. All right, so we know we're going to run 30. And we know we're looking to beat 9817, right? Because we know how to get to 9817. Okay, so there's a 9822, right? That's an improvement. There's a 9837. Nine eight two seven. 9835. That's a new high, right? 9835 on Epoch 20. Okay. A second 9835. 9837. Okay. All right, so here we are. Okay. Look at column 7, guys. Column 7 improved. Column 9 absolutely improved, right? We're making virtually, well, not virtually zero. We're making a lot fewer errors in 9. And 8 seems kind of sort of unchanged, you know? It's still making quite a few errors between 8 and 5. But now we have more errors over here. We have two 11s over here, right? Better model. We beat our baseline, right? We got up into the 983s. So our hypothesis essentially was correct, right? That we could kind of just give it more time, right? You could argue that it still could use another 50 epochs, right? Because it was still kind of sort of in that upward direction. It hadn't stalled out yet, right? What do you guys think? Are there any observations I'm missing here? What do you guys think? Anybody else want to give their observations? While you guys are thinking about that, I'm going to go to ChatGPT and figure out what we need to do to adjust our learning rate. Okay, there we go. It's in the optimizers atom. And it is suggesting a learning rate of 0.001. Does anybody want to opine on that? I need the whole line. What do people think about 001? What do you guys think? Let me know in the chat how you feel about the learning rate of 001. Osama says it requires more time. Yeah. Yeah, right? 001, pretty low value. So it's not gonna be fast, right? Yassine says I think it should be better. Yeah, Yassine. I mean, I think there's reasons to believe why it would be better, right? Again, nothing is guaranteed, but we can have a reasonable expectation that things are gonna go well for it, right? So let's try this. Because I think Dendelson is making a good suggestion there, right? We haven't played it all with we haven't played it all with the learning rate. So this is not going to be fast, guys. Not going to be fast. And what is the baseline? I think 9837, I believe, is our new baseline, right? We can basically say we know how to get to 9837. So any new effort would have to kind of best that, right? All right, there's a 9832. Okay. Um oh wow. That is interesting. Anything jumping out at you guys on this? Wow. Oh wow. What is jumping out at you guys on this? Oh wow, there's so many things happening on this chart. What do you guys think? Yeah, wow. This is crazy. But remember, technically we did get we got a result slightly lower than our baseline. Yeah, yeah, Yassine, what's going on? Yassine's right. What's going on with number 3? Jeez. Look at that. 3 is terrible now. On the other hand, look at 8. 8 is near perfect now, right? 7 is not terrible. There's 7 and 2 still have problems, right? Manoj says 3 is terrific. No, Manoj. I mean, I don't think you're being sarcastic there. But no, Manoj. 3 is actually doing terrible in this run. But yeah, guys, I mean, this is not great, right? We basically have just exchanged one set of problems for another set of problems, right? So that's one of those things where we need to kind of realize that improvement isn't in the macro values, it's also in the details, right? So, what else? What else do you guys want to try? Let's go through one more iteration. What is another iteration that we could try here, guys? One parameter, Yassine says, one parameter I think we can adjust as well as a filter size in the convolutional layers. Help me understand what you mean by filter size there in that scenario, Yassine. I'm not 100% sure what you mean by that. Help me understand that. And for those of you that just want a quick reminder, right now we're still kind of using like that cone or that funnel shaped architecture that ChatGPT had initially requested, right? I think another thing we should try is, did you guys notice how it's a little bit unconventional that we're going from these 784 inputs immediately down to 512? Or even what? Initially we were going down to 128, I believe, in the very first model. What if we went up instead? What if we went to like 1,000 instead? Right? Something where our hidden layer has more nodes. And again, I'm just kind of making conversation here because any approach is valid. You don't really know what the answer is going to be, right? Only thing we know is that we have 784 inputs in our initial shape, and that we're going to have 10 nodes in our output layer. But that's it. Otherwise, everything else is up to us, right? In the convolutional layer, each pixel considers a number of pixels around it. Filter size controls how many surrounding pixels. 3x3 filter considers 3 on each side. We can do 5x5 or something else. Okay. I could see that. I'm tempted to just try something around the size of this first layer. Because think about that, guys. We're going from 784 down to 512. What if we did this? We haven't tried this. We've tried an even neural network, but even then, the first layer was going from a lot of inputs to a smaller number of inputs, right? I think we did it at the 256 level. What if we try this? Rid of this. Let's try. Yassine says we can also add some max pooling layers. Yeah, sure. But look, guys, it's my intent that this is going to be the last iteration we're going to try here. Because really, I mean, we're not trying to solve the MNIST data set, right? What I'm really trying to impress upon you guys is that this is the work of a data scientist. Everything we've done for like the last hour is data science. Because our code has generally stayed the same for the last hour and a half, right? But it's about trying the different approaches, the different settings, the different interpretations of the results and saying, well, wait a minute, well, that one could benefit from more time. Oh no, that one was going terrible from the beginning. That's really kind of like the lesson here, right? The lesson isn't how do we solve MNIST. The lesson is saying, hey, look, I mean, what we're doing now, like this is the job, guys. Like this is what you do as a data scientist, right? More specifically, as a data scientist working with neural networks. So whenever I hear people like, sometimes, they kind of poo-poo this portion, or they don't understand the difference, they don't understand what data scientists do on a daily basis, so they don't understand, well, what do you mean you need to know code or whatnot? Well, this is it, right? This is like what you do as a data scientist. This is the experimentation side of the job, right? We're going to do a little bit more of that next week when we talk more about the grid searches. And then also we got to keep tracking this. We got to start tracking this, right? Right now we're kind of sort of feeling our way along, and we're doing a good job of that. And maybe it helps that we're in a group. But when you're alone and you want to kind of like document your work and tell people, hey, I took your data, I ran 27 experiments, here's the result. Like, we need to be a little bit more organized, right? So we're going to do that, right? We're going to do that in some of our next efforts, okay? But let's see where we land here. We're at 9832, which is not terrible. But again, guys, this is the job, right? If you're not enjoying what we're doing now, then like I don't know what to tell you, because like this is what you do as a data scientist. So this is showing kind of sort of signs of promise. So this is our slowest training network. And it's also our biggest network because you're going to have a lot more weights, right? You're going to have weights for every node of every layer. And this is our biggest network so far, right? Another part you should be taken from, you should be kind of taken away from this is that, guess what? More layers, more nodes is not always more better, right? And we kind of saw that before in our previous efforts, but it should definitely be cemented today. Think of all the different efforts that we've done just now and the different architectures, and the accuracy rate has moved 0.003, right? We've been in a range of 0.003, like 98 something. We've been in that range for like the last 45 minutes, right? So it's not always more is better. Data, can kind of be nuanced in that way. There we go. There's a 9857. We got a 9857 in our 24 of 30 epochs. $9,845. That's good. So we're making incremental progress. Doesn't mean that every class is going to look great, but this is a little bit more encouraging, right? $9,852. 9852 is a pretty good result, guys. That's one of the highest ones we've seen. All right, so this is the last confusion matrix we're going to look at. What do you guys think? Okay. Okay. Let me know what you guys think. A couple of things are catching my eye. Yeah. I'm gonna go ahead and say that this is one of the better confusion matrices we've seen. I'm gonna also go ahead and say that I can tell a difference in the accuracy, right? Because remember, the accuracy that we're looking at during that training cycle is kind of like a macro number, right? Better. Osama says better than a previous model. Osama, I agree, right? Like you can feel a difference in the accuracy here, right? Yassine says everything has improved except only number 4. Yeah, right. I mean, this number obviously jumps out at people, right? But guess what? It's our only double-digit number, and it's a fairly low double-digit number, right? We've had charts with just one double-digit number, but it was a 15, right? Here it's an 11, so that's not horrible. Look how improved 9, 8, and 7 are. I mean, 9 is pretty good. 7 is nearly, 8 is nearly perfect now. 7 is also nearly perfect, right? Remember, guys, we just a couple of versions ago, we had a model where 7, 8, 9 were horrible, right? So that's an improvement. Manoj says better than the previous baseline model. Yeah. And you know what, Manoj? I like the way you put that because, like, you know what? That would be a good t-shirt for data scientists, right? Better than the previous baseline. Like that's your whole goal. Like that, when people ask, like, what do data scientists do? That's what it is. Like, what is my baseline and what am I going to try to beat that baseline, right? That's the life of a data scientist, right? But yeah, Manoj. So more importantly, Manoj, it's not just numerical. I think that just to the eye and the different numbers, sections, or combinations that each of us has been keying in on are pretty good. Osama says 5 is also good. Yeah, yeah. I mean, 5 is near perfect. Well, 5 and 3 are still a little problematic, but 5 is very good. You're right about that. But yeah, guys, I mean, like, it feels like this is like just a better model, right? Yeah. I mean, look at 8. 8 is like basically perfect, right? Same for 7. I mean, 7 is as good, is nearly as good as you're going to get, right? So here's another thing, right? This is another scenario where, hey, look, maybe 30 epochs is not enough. What do you think would happen if we went to like 100 epochs, right? Like, maybe let's go ahead and run that while we're talking. Can I do that? I think I have to get rid of this. But what happens if we just go to 100 epochs while we're still talking? Just So this is one of those scenarios where you might run experiments and then you're writing things down for what you want to do over the weekend, right? And then on Friday, you would write up all your experiment, or tee up all of your experiments, kick them off, and then give it 2 days, 3 days, whatever, a long weekend or whatever you want it to be. And you come back and you say, okay, well, let me see what more time did to the model, because sometimes we might kind of shortcut ourselves if we say, oh, we have to sit here and we have to watch the machine and whatnot. Sometimes just kick off the experiment and let it fly. See if it can get you somewhere, to get you to a place better than where you thought you could be, right? So I think that we're really kind of like on the right track here. Again, not to solve mints, but to appreciate the work that goes into, being a data scientist, right? I mean, everything that we've done here is what you would do on a day-to-day basis. And keep in mind that when I say that, I mean that I mean that also beyond neural networks. We happen to be using neural networks today, but you could be repeating this with any technology or library or approach or whatever else you want, right? It's just the experimentation would just be with different data and different models, slightly different settings, but it's all still, the spirit of experimentation of data science. Right? All right, so we're going to go ahead and let this fly, let this run a little bit. Give me, if you guys want, we'll do a couple of, if you guys have any other questions, let me know. But otherwise, what I'm going to do is I'm going to do the same thing I did last time, where I'm going to post these results on my Instagram and on YouTube in the community section of YouTube or whatever it's called. But I think that, this is on the right track here. Denelson says, sorry to get off topic, sir, but I just checked my LinkedIn, but I was unable to find your message. Okay, Denelson, I'll send you something else. I think I had sent it as part of one of your posts or updates or something, but let me resend it. But yeah, but if anybody else has other questions or if something didn't make sense, now's a good time to ask. Otherwise, I'm going to keep an eye on these epochs. Who knows? Maybe we can get into the 9/9s, right? Because that could be another way to approach this, where your whole goal is to get to a 9/9, and you could say, I'm going to run a bunch of different experiments. I'm going to run a bunch of grid search settings, but stop if you're not on your way to 9/9 after 50 epochs. That's a valid approach, right? You could be saying that's the concept known as early stopping in training, right? Where you can say, well, look, this is not headed in a positive direction, and I already know my baseline is up here, so let me save my processing power down here and start a new experiment. Totally valid way to go about that, right? Oh, guys, we went for almost 3 hours today. You guys are insane. You guys are mean for making an old man like me go for almost 3 hours. You guys are crazy. All right, guys. So let's see where this last model ends up. But I want to thank you all so much for being a part of today's class. Really good stuff, guys. And we're going to build on this next week. We're going to build on this with more formalized grid search, with more formalized documentation, right? Because right now we're just kind of, going off the cuff, just trying different things. But, you got to be able to kind of document all of your experiments. This also helps you a little bit with your stakeholders. It helps you get a little bit of credibility to be able to say, hey, look, my team took a look at this. We spent 2 weeks at this. We ran 700 experiments over 2 weeks, and this is where we're at, right? That's a very powerful, not just a story, but it's a powerful way to show your professionalism and say, hey, look, we are scientists working in a lab. The lab just happens to be, made up of code, but we ran this many experiments, and here's where we're at. That's super powerful for a almost like a legitimacy in front of your stakeholders. Okay. All right, everybody. So thank you so much. I can't believe we almost went 3 hours. You guys are crazy. Thank you for sticking in there with me. Really appreciate it. As always, we live in such a dynamic world, and I worry about every single one of you because I know we have people from all over the world here. So thank you so much. Please, watch out for yourselves. Take care of yourselves, take care of your families, and I'll see you guys next time.